Okay, you guys can see my shared screen.
Let's see. Let's see.
Yes, sir.
How do you see the shit? Oh, there. Yeah. Yeah, I see it.
So you're looking at my screen. All right. Um, 2.1. So this question.
Yeah. Everything else I
Right.
did.
Right. So before we get to that question, I want to find out from you guys if there is any question regarding these two questions on precision measurement. Do
This
we have anyone on the floor who has a question on precision measurement?
especially say maybe if you can just assist on this one that you've just projected there. I struggled getting through this one. The second one I didn't have a problem, but this one I was struggling.
Okay. So let's do this
Excuse me.
one quickly.
Yes,
Right.
please.
In fact, with precision measurement, once you get your angles right and you know exactly what you are looking for and how you are going to get it, everything else becomes math, basically.
Yeah,
Right.
this way I was stuck with where do I position my angles, the
Okay.
triangle especially.
All right. We will do that quickly.
Yeah,
Right.
thank you.
As far as having to label this one, you guys were able to label from number 1 to number 4.
Yes.
Yes, sir.
Should I read out my answers?
Now let me do that. Nah?
Okay. Okay.
So you guys can check your answers. So number 4 is a straight edge. Right. Number 4 is a straight edge. Number 3 is a
Oops. I did.
gauge block. Gauge block as in gauge. So gauge block. Right. So number 3 is a gauge block. So number 4 I said is a straight edge. Right. Number 2, you can simply just call that a roller. Right. Roller or precision roller. That's fine. And then number 1 is a V block. Right. So with number 2, you can either have precision roller or just roller. It's fine. Right. Now as far as angles, how you work out angles here. Right. You've been given this 60-degree angle. Right. And if you look here, this angle is, what do they call it? Vertically opposite with this one. So if this is 60
Yes.
degrees, it means that 60 degrees as well, right?
Yeah, that's fine so far.
Right. Now if you look here, you have two tangents. This line and this line are touching this roller once, meaning that you can take this line and this line as tangents. Right. So now if you watched my
Mhm.
videos, right? If you watch my videos, I said that if you have two tangents meeting at a common point, right, those the angle that is formed between them is essentially an included angle, right? Because if you split the two tangents into two equal halves, right, the angles you get on either end. So meaning, um, so that's that center line. If you look at the center line, right, it cuts at the middle, right, of where the two tangents meet, right, meaning that this angle and this angle are half of the 60 degrees, right? So meaning that that's 30 degrees and this here is 30 degrees, right? What else do you know? You know that if you draw a line from the center of a roller, right, to the tangent, you have an angle of 90 degrees there, right? As soon as you draw that line, you inadvertently have this right angle triangle. Do we see that? Hello,
Yes, sir.
can everyone see this?
Yes, yes, sir, we
Yes,
can.
sir.
Right, so you inadvertently get that right angle triangle, right? Now this triangle, let's call this, let's say that's A, call this B, call this C, right? Call it D, all right? Now if you look here, we are looking to determine the value of H, right? If you look at H, right, if you project H on this side, or if you project the distance between H and 50 millimeters, right, that is equal to the A. So if you look at AC, right, if you look at the distance from A to C, right, it is equal to the distance from here to there. Can everyone see that? Right. If you look at the distance,
Yes, sir.
right, AC is equal to this whole distance. Right. So you can say AC is equal to H plus
AB
the 50. Right.
H.
Are we together?
Yes, we're together.
So that means to be able to get AC, you must have calculated AC. I mean, to get H, you must have calculated AC, right? So you need to calculate this whole distance. Now, aside from this algebraic expression, AC is also equal to AB plus BC, right? AC is also equal to AB plus BC, right? Meaning that to get AC, right, you need to have calculated AB as well as BC. Now, if you look at AB, right, AB is also equal to what? It's also equal to the radius of this roller. Can we see that?
Yes, sir.
Right. So meaning AC is equal to the radius of the roller plus BC. Right. Now they did give us, in fact, they did give us the diameter of the roller. They said it's 40 millimeters. Right. Now with precision measurement, right, it is preferable that you leave your units as millimeters. Right. You don't necessarily have to have your units in meters. Nah? So if the diameter of the roller is 40 millimeters, it means its radius is what? 20 millimeters plus BC. Now, what does this tell us? It means to get AC, we need to calculate BC. Here is BC, right? Now, if you look at BC, BC is part of this right-angled triangle, right? It is the hypotenuse, in fact, of this right-angled triangle, right? So we need to come up with an expression using this triangle that will help us calculate BC. Right? Do we see that? Hello?
Yes, sir.
Yes, sir. Yes, sir.
Right?
Yes, sir.
So
Yes, sir. We see it.
looking at the right angle triangle, right? In order to be able to calculate either an angle or a side of a triangle, right? You need either another angle, but you need two quantities, right? Either two sides, right? Or you need a side and an angle. Now, in this case, we have this angle and we have this side. Because remember, when drawing a line from the center of the roller to where this tangent touches this roller, or where this line touches the roller, so the tangent, right, that line, right, is equivalent to what? Is equivalent to the roller's, what is this, radius. So if this is equal to the radius, it means we have this side, because we know that the diameter of the roller is 40 millimeters, meaning its radius is 20 millimeters, right? So essentially, we know that this is equal to 20. So we have a side and we have an angle, right? Now, based on the fact that we need to use this triangle to calculate this side, right? In using this angle, right, we look at the sides that we have. The one side that we have is opposite the angle. The other side is the hypotenuse, right? So of the three trig ratios that you can use here, right, we can only use one based on what you've been given, because the angle we have, or the side we have, right, is opposite the angle, and the side we're looking for is the hypotenuse of the triangle, right? So meaning that from the three trig ratios being sine, cos, and what is this, and tan, we are only able to use sine here, right? Because it is with sine. Remember, sine. Okay. Remember, sine theta is equal to what? Opposite over the hypotenuse. Right. So opposite here is that 20. The hypotenuse is BC. Do we see that?
Yes, sir.
Yes,
Right.
yes, yes.
And theta in this
Yes, sir.
case, theta is in this case is 30 degrees. So this will be sine 30 is equal to 20 divided by BC. Right. Now sine 30 is equal to a half. Right. This is equal to half, which is equal to 20 divided by BC. And from here, you solve for BC. Right. Solving for BC, you cross multiply. Right. And in cross multiplying, BC is then determined to be 40 millimeters. All right. Once you've determined BC being 40 millimeters, you substitute it here. 40 plus 20 gives us AC, so AC is 60. Substituting AC here being equal to 60, you transpose the 50 and H is equal to 10. Are we clear?
Yes, sir.
Yes, sir.
Right. With precision measurement, once you've figured out what you are looking for, you've worked out the angles, and you figure out what it is or the approach you need to take to get what you're looking for. That's pretty much it. Meccano at that point will be done, right? From that point, it will just be maths. Do we have any more questions? Hello, people.
No, sir.
Okay,
So,
Minar, so,
yep.
So when you're constructing these triangles, you need to ensure that they're both sitting on the tangents, ne? Because like you know how I did it, I took my straight line and I make it as like you see your 90 degrees is sitting at a slight angle, but mine's are just drew it straight across. So now it didn't give me, and then I just drew the line going to C. So now it doesn't give me this exactly how. So now you need to ensure that it's sitting on the tangents, ne?
Yes.
Your triangles.
Yes. So if you look at my videos, there's a reason for everything that you are doing, right? Because remember, here we are trying to, what we are trying to accomplish is to teach you engineering concepts, right? So everything I do is based on engineering concepts, right? Even how I constructed this triangle, it was based on laws of congruency. Remember, I explained congruency
Yeah.
in one of my videos.
Yeah, I remember.
Yeah, so it's based on that. So unless you can justify what you are doing, do not take that approach. In whatever approach you take, in any of the problems in Meccano, right? They have to be justified by an engineering principle.
Okay, well, makes sense.
Yeah.
Okay, thanks.
All right, cool. So any more questions on this one?
No, sir.
Wonderful.
No, sir.
No.
Okay, cool. Right. I would think everyone was able to do this one. I think there's a video on a problem that is similar to this one, or is it exactly this one? I'm not sure. But there's a video in one of your videos that I uploaded on Moodle that is similar to this problem.
It's a similar one, sir.
It's a similar one.
It's just a change of its diameter only, but
Yeah.
it's the same principle. Is the same.
Yes. Right. So I guess we can move on to this one. One of you asked a question regarding 2.1. Ross is still around. Where's Ross?
His mic is muted, sir.
Was I muted this entire time? I was trying to talk and see if the final answer for H was 10 millimeters or something. Sorry.
Yeah,
This is my first time. Yeah, it's my first time doing this. Sorry, guys.
Cool.
Okay, cool.
So so the answer for H is 10. Yes.
Yeah.
Right.
Okay, just
So,
wanted to confirm.
yes. So let us go through 2.1.
Yeah.
Right. So let's go through 2.1. Now 2.1 is based on hydraulics. Now hydraulics is quite lengthy, right? There's a bit of units that we need to cover there, right? One of those.
Okay.
The very first one is essentially applying Bernoulli's principle, right? Without
Yes.
necessarily considering any losses, right? And then the
Okay.
second unit is based on us considering losses. In fact, what is this? Frictional head losses, to be specific, right? So HF, frictional head losses. This is the second
Yes.
unit where we consider frictional head losses, HF, right? Now, when we
Okay.
consider frictional head losses, there's two methods that we can use, right? You can either use Darcy's equation, right, or Darcy's formula, or we can use Chase's formula, right? In using either of those methods or formulas, right, we should be able to get the same thing.
Okay.
Right. So in using Darcy or Chase's formula, you should be able to get the same thing.
Yes, sir.
Right. So meaning there is a formula for calculating. There's a formula for calculating the frictional head loss using Darcy's formula. Right. Using Darcy's formula, HF is equal to 2 times F times the length of the pipe
Times the length of the pipe
times I think this is
T
V squared divided by
T
what is this?
times the
GD.
diameter.
G times D.
Yeah.
You guys can see this, right? So using Darcy's formula, this is how we calculate. Using Darcy's equation or Darcy's formula, this is how we calculate HF, right? Which is the frictional head loss. Now we use this one if we have the velocity of the water running through the pipe.
Yes, sir.
Right? But if you have the flow rate instead, right? If you have the flow rate instead, you can use this one. You can use what is it? I think F times L times Q squared divided by 3, I think 0.26 times the diameter of the pipe. So the diameter of this pipe to the exponent 5. Right?
You
So excuse
called
me.
that.
Sorry?
You called that flow rate variation, right, sir?
Nah, I just call this the flow rate. This you can call either a flow rate or a discharge. Right? So discharge and flow rates is the same thing.
Okay.
Right. So the velocity, if you've been given the velocity of the water will be in meters per second, right? Whereas the flow rate, Q, right? So Q will either be in liters per second or meter cube per second, right? You must always use it in cubic meters per second. So meaning that if you've been given Q in liters per second, you should convert it to cubic meters per second, always. So the one you substitute here must be such that it has been converted.
I'm back. Okay.
You with us?
Sorry, I got disconnected for a second there. Could you repeat off to what you said after flow rate? Yeah.
Right. So I said the flow rate. So the velocity of the water is in meters per second, right? The flow rate, however, is in liters. Can either be in liters per second or cubic meters per second, right? Sometimes they'll even use liters per minute, right? Either way, you must always use it in cubic meters per second, So when you
Yes.
substitute it here on this formula, right, you must substitute it such that it is substituted in terms of cubic meters per second. Right? Right. So if you've been given the velocity of the water, this is the version of Darcy's formula that you use. But if you've been given the flow rate or discharge, then this is the version of Darcy's formula that you can use. So these two are variations. This is the velocity variation. This is the flow rate variation of calculating the frictional head loss.
Okay.
Sorry, sir.
Yes.
I have a question for the flow rate for velocity variation. There is no 4 in the formula.
So there's a 4 if you do this, right? If there's 4 here, there's going to be 2 here. So
Oh, it's
mathematically,
simplified. Okay, okay.
yes.
All right. Yeah, I see.
This is just
Thank you.
the easiest way of doing it.
Okay.
Right? You can have 4
Thank
there, that's fine. But if you have 4 here, there's a 2 here.
you.
So all I did was essentially simplify that.
Yeah. All right. Thank you, sir.
Yes. Right. Now, whichever variation you choose to use doesn't matter. It's going to give you the same thing. Right. Hence, I'm saying I gave you guys both variations, right, for convenience. Right. Now you know if you've been given Q, you can simply just use this variation of calculating the frictional head loss as opposed to using the Q to calculate V and then using this one. You see what I'm saying?
Yeah, okay.
Are we together here with everyone?
Yes, sir.
So
Yes, sir, we're still following.
Right. Okay, so let's attempt the whole of 2.1. Right.
quickly, sorry, sir, but when will so how we figure out whether to use the flow rate variation and the regular formula will come to how it's asked. What would an example of that would be?
It'll come down to if you've been given Q or V. Like for instance, if you look at this one, we've been given Q. So because we've been given Q,
okay.
to calculate HF, we'll simply use this variation.
Oh, okay. Thank you, sir.
But if you are comfortable with using this one, then all you do is use the Q. Remember, Q is equal to V times A, right? So you can
All right.
calculate V from this formula. You will have Q, the area you will have, because they will have given you the diameter of the pipe. So you can work out V and then use this one if you are only comfortable with using this one, right? I'm giving you both variations for convenience. Instead of, for instance, because you've been given Q, instead of having to calculate V first, right, you just use this formula. It'll give you the same, what is this? The same frictional head loss you will get when using this one.
All right.
Any more questions? Right, let us continue.
Right.
Now let us look at how we would attempt such a question, right? Let's see what you've been given. A horizontal pipeline with a diameter of 90 millimeters conveys water at 20 liters per second with a pressure drop of 50 kilopascals per 20 meters of pipeline, right? So based on what you've been given, you know straight away that you are potentially looking at a problem based on either the first unit where you do not consider where you do not consider
Frictional losses.
Yes, frictional losses, right? Or the second unit where we consider frictional head losses. That you will see from the questions, right? If you look at 2.2.1, calculate the value of the coefficient of friction Once they ask you to calculate the coefficient of friction, it means we are considering losses, right? If we are considering losses, right, that is a tell that you are looking at a Darcy or Chase's formula kind of problem, right? So they said calculate the coefficient of friction using Darcy's formula, right? Now, as much as Darcy and Chase's formula will essentially give you the same the same frictional head loss. If they've specified for you to use Darcy's formula, then you must use Darcy's formula. Are we clear?
Yes, sir.
Because there is another equation to
Things
calculate
quite
F.
jittery for me.
If say you've been given the coefficient, Chase's coefficient, right? Using Chase's coefficient, this is c squared is equal to, I think, 2g over f. Or is it the other way around? No, I think it's 2g over f. Yeah, 2g over f. So you can also calculate f using this formula, but this formula is for Chase's formula, right? So if they've specified that you need to calculate f using Darcy's formula, it means you cannot use this one to calculate f because this is based on Chase's formula.
So you lose that 5 marks immediately, sir.
Yes. If you use Chase's formula and you were told to use Darcy's, we don't even look at that.
100%.
You lose the whole
Oh,
5 marks.
okay.
Are we clear?
Yeah, boy.
Yeah. Okay.
Right. So when they say using
Didn't get a lot
Darcy's
of what you
formula,
said, but no.
when they say using Darcy's formula, right, it then means you're essentially going to use one of these. Right. If you use this one, there's F. If you use this one, there's F.
Okay.
Right. Now, based on what we've been given here, right, based on what we've been given, they said calculate the value of F using Darcy's formula. So using Darcy's formula, because we've been given Q, I am going to use this variation of calculating the frictional head loss because I have
flow variation.
right. We have Q, we have the diameter of the pipe, we have essentially the length of the pipe. I'll explain the length of the pipe just now, and this is what you'll be looking for, right? So it also means that in using this formula, right, you also must have calculated HF. So we are going to calculate HF using what? Using the pressure drop. Remember, in one of the videos, I said with Darcy's formula, there's essentially three scenarios, right, that you can expect, right? One of the first scenario was if you have two reservoirs connected with a pipe, right? The difference in water levels, right, will give you HF. Do you remember that?
Full disclosure, I didn't get around to watching the video. I'm a little behind on that.
It seems you are not the only one.
I remember this. I remember it.
It seems you are not the only one. You guys must watch those
Yes.
videos. Those videos are very
As you
informative.
remember.
I did watch your precise measurement videos and the first videos on hydraulics, but not the last ones.
Yeah, so I think there's like 7 or 8 videos on hydraulics, and it only covers just 2 units, right? So if you haven't watched the videos, make sure you watch the videos before test 2. I will be adding more videos there where I'll be covering measurement of flow.
Okay, sir. Well, will the hydraulics and precise measurement be in test 2 as well?
Yes.
Oh, okay. Just checking.
Yes. So for test 1, we only covered, for hydraulics, we only covered applying Bernoulli's as well as Darcy and Chase's formula. For the second assessment under hydraulics, you can expect measurement of flow.
Ah, okay.
So there'll be a question on measurement of flow, right? Probably only measurement of flow. I'll decide and let you guys know once I've decided, right? Because after Darcy and Chase's formula, we have measurement of flow. Under measurement of flow, we have flow through an orifice as well as flow through a venturimeter. right?
Okay.
So I could decide to just have those 2 units for the second test,
Right.
right? So when I tell you guys to watch the videos that I upload on Moodle, make sure you watch them. They are very informative.
Yes, sir.
Yeah? Right.
Yes, sir.
So under Darcy-Chase's formula, there's 3 scenarios, right? One of the scenarios is where you have 2 reservoirs connected with a pipeline, right? Those 2 reservoirs are such that they are at different water levels, right? Now, in calculating HF, we then come to the conclusion that when you have 2 reservoirs, right, at different at different water levels, right, the difference in water levels then becomes the the HF, right? So meaning that
Yeah.
HF in that scenario, HF is equal to the change in H, right? Or maybe you guys call it change in Z, the difference in water levels, right? In that kind of scenario, right, HF is equal to the change in water levels, right? And then you
Okay.
get the second scenario where you have a horizontal pipe that has a a constant diameter,
Okay.
right? Which is this case here, right? So I said you have 3 scenarios. I mentioned the first one. The second one is if you have a horizontal pipe that has a constant diameter, right? And then the third one is if again you have 2 reservoirs connected with the pipeline, right? But with this one, the water levels, right, are in the same level, right? So the third scenario you treat as you would treat the second scenario, which is the one for the horizontal pipe,
Oh.
right? So the last 2 scenarios you treat the same way because essentially you are just looking at the horizontal pipe, right? Because with both scenarios you are given a pressure drop, right?
Okay.
Now you have a pipeline, right? You have a pipeline. The pipe is such that it has a constant diameter, so it's not a tapered pipe, right? It has a constant diameter, meaning that even the velocity of the water running through the pipe, right, is going to be the same throughout. Hence, for a horizontal pipe, we call the velocity average velocity because it is more or less the same throughout. Hence, seeing that there is no change in diameter, right? Because remember that the velocity of the water is closely linked to if the pipe is tapered or not, right? If the pipe is tapered, it means that there'll either be acceleration or deceleration. And because of that, there has to be a change in velocity, right? Hence, we only get the change in velocity if the pipe is tapered. But if the pipe is not tapered, hence it has a constant diameter, right? The velocity of the water running through the pipe does not change. Are we clear?
Yes, sir.
Yes, sir.
Right. Right. So what tends to happen here is seeing that the pipe is horizontal and there is the diameter is constant, right? The pressure varies due to the what do they call it? Due to the shear stresses on the pipe walls, right? So meaning that as the water, say the water is going in that direction, right? If the water is going in that direction, you can take this as 1, take this as 2, right? As the water flows in that direction, right, it essentially loses pressure. Why? Because of the shear stresses on the pipe walls, right? Now, what we've been given here, they said that with a pressure drop of 50 kilopascals per 20 meters of pipeline. Now, they haven't necessarily given us the length of the pipe. What they've given us, though, is that with every 20-meter of pipeline, there is a pressure drop of what? Of 50 kilopascals, right? So however long the pipeline is, right, for every 20 meters, there is a pressure drop of 50 kilopascals. So meaning essentially, seeing that we're going to be using the 50 kilopascals, we can make use of these 20 meters as our length, because we are only concentrating on the 20 meters of pipeline.
Okay.
Are we clear?
All right. Yes, sir.
Right. Now with this one, with this scenario, right, when you've been given the pressure drop, right, that pressure drop is essentially equal to HF. Right, so to calculate HF, if you've been given the pressure drop on a horizontal pipe,
Okay.
it'll be equal to the change in pressure divided by rho times G. You see what I did here?
I think so.
Yes,
Right? If you've been given
Yes,
the
sir.
pressure
Yes, sir.
drop, remember, pressure is equal to what? Rho GH. Right? So essentially, change in pressure is then, if we work out, if we were to apply Bernoulli, right, on this horizontal pipe, right? If we were to apply Bernoulli's on this horizontal pipe, right? In fact, maybe let us do that quickly, because I see some of you seem confused there. You see, this is what happens when you don't watch my videos. Now, let us say you apply Bernoulli's. When you apply Bernoulli's, right, you apply Bernoulli's between 0.1 and 0.2, right? So on 0.1, you'll have P1 plus, what is this, half rho V1 squared plus, what is this, rho G, is it rho? No. Yes.
Row
H.
row 1.
GH1
Yeah,
is
row 1
equal to
P2
P2
plus half PV2
plus half
squared
rho V2 squared plus rho
plus
G
row 2.
H2. Right? Now from this, because the pipe is horizontal, remember the H is measured from the ground to the center line of the pipe. Right? So essentially H1 and H2, seeing that the pipe is horizontal, right, is going to be the same. So this and that mathematically is going to cancel. Right?
Yeah.
And then seeing that there's the pipe has a constant diameter, right? The velocity is average, meaning it is the same throughout the pipeline, meaning that V1 and V2 are essentially equal. Hence, mathematically, they're going to cancel each other out. All right. Now I forgot plus rho G. I forgot plus rho G HF. But remember, we are considering losses.
Oh,
Hence, you must have the rho G HF.
that's new. Okay.
So it's new because you didn't watch my videos.
Okay.
Right. Remember that in applying Bernoulli's, we use this if we are not. Let's remove this for now. So we make use of this version of Bernoulli's if we are not considering losses. Once you consider losses, then you must have HF. Are we clear?
Yes, sir.
Yes, sir.
Right. So now what you have, remember what it is that you're looking for from applying Bernoulli's. We're looking for HF. So what you will do is you transpose P2 to that side. You transpose P2, right? P2 to this side, right? Hence you'll be left with P1 minus P2 is equal to rho G HF, right?
Okay.
Now, remember, we've already established that as the water goes in the direction of flow, right, the pressure decreases, right? So meaning what? Meaning that P2 is greater than, meaning that P1 is greater than P2, right? If that's the case, it means that P1 minus P2 is essentially the change in pressure, which is what you've been given. So P1 minus P2 is essentially the change in pressure is equal to rho G HF. And then because we're looking for HF, You then divide both sides by what? By rho g. Right? If you divide both sides by rho g, this here is what you get. Now in the video, right, I said because we've already established that if you apply Bernoulli's, right, HF will essentially be equal to this. There is no need to apply Bernoulli's. You can start your solution from here. Are we clear?
Yes, sir.
Yes, sir.
Hello?
Yes.
Where's
Yes,
everyone
sir,
else?
clear.
All right.
Yes, we yes, sir.
Oh, yes, sir.
Yeah, say something.
Yeah, sure.
Because you guys didn't watch the video. Yeah. So
Yes, sir.
this is just for context so that you guys understand where this comes from. But after having understood where this comes from, you don't need to do this because we already know in doing this, this is where it is headed.
Oh,
That is why
okay.
I explained the concepts of Darcy and Chase's formula using those three scenarios, so that you know how we calculate HF when looking at the first scenario, how we calculate HF when looking at the second and third scenario. Right? So essentially HF is equal to the change in pressure divided by rho g. Now the change in pressure is the pressure drop. So essentially we've been given the change in pressure. So meaning that HF is equal to what? The 50 kilopascals, so times 1,000. Remember that the pressure you need to express in pascals, not kilopascals.
Okay.
That is why you have to divide this by 1,000. I mean, multiply it by 1,000. So instead of using 50, we say 50 times 1,000. Right? So 50,000. Right? The 50 kilopascals is 50,000. 50 kilopascals is 50 pascals. Is 50,000 pascals, sorry. Right? Divided by rho g. Rho of water is 1,000. Right? Times g. G for Meccano is 9.81. Right? So for Meccano,
Okay.
G is 9.81, not 9.8, like in science.
Ah. Okay.
Right? And then you get whatever you get here. So we won't be doing the calculations. I'm just taking you through how we approach such a problem.
Okay.
Any questions?
No,
So
sir.
sir, when it came to the, so I see this question is worth 5 marks. Did we have to do all this calculate to show all this, how we substitute all of this to get HF, which is the change in pressure of you know?
So remember, you're not looking for HF, you're looking for F. So once you've calculated HF, then you go to this formula to calculate F.
Okay.
So this here is like 2 marks. So the other 3 you will get from using this formula to calculate what we are looking for.
Okay. Okay.
Sorry, sir, I have a question.
Mhm.
In the formula there, because we're equating, is matter if maybe I can say P1 instead of P2, or P1 is the initial one, P2 is the discharge side. How to determine is 1 or is 2, or doesn't matter?
You see, this is why you must watch my videos. All of this is explained in my videos. P1, I mean, the one side, right, is the entry side. The 2 side is the exit.
Okay.
So if water enters on this side, then you know this side you are going to denote as 1. And
As
where it
well.
exits, that side you denote as 2.
All right.
So 1
Okay.
stands for entry, 2 stands for exit.
All right. Thank you.
Right? Right. So I'm going to erase all this now.
Okay.
Yeah?
Oh, the answer for HF is 5,097.
Okay. So I don't really care about the answer.
Okay.
I'm just taking you through how you would approach such a problem.
All right.
Okay?
Yeah.
Right. Oof. Right. So once you've calculated HF, right, now you can calculate what you are looking for, the coefficient of friction, right, using this formula, right? So you would use HF is equal to F times L times Q squared divided by 3,026 times D to the exponent 5, right? So this is the formula that you use, right? And then Q, remember, you need to substitute as cubic meters per second, right? So here we've been given liters per second, right? And how we convert from liters to cubic meters is you divide this by 1,000, right? So essentially here, seeing that this is in seconds, so the time is in seconds, so that you're gonna leave as is.
Okay. Yeah.
To convert from liters per second to cubic meters, you divide this by 1,000. Why? Because to convert from liters to cubic meters, right, you divide by 1,000. To convert from cubic meters to liters, you multiply by 1,000. So from liters to cubic meters, you divide. From cubic meters to liters, you multiply. Right? And what you get here will be in cubic meters per second. And that's what you use in substituting here. Right? At that point, you will have calculated HF. So you will have HF. L, the length of the pipe. We've already established that, seeing that we're only concentrating on 20 meters of pipeline, right? That is what we are going to take as our length. Q, you've been given. All you do is convert it to cubic meters per second. Diameter of the pipe, we've been given. So essentially, you are just missing this here, which is what you're looking for. And you take any mathematical approach to calculate this. Are we clear?
Yes, sir.
Yes, sir.
Right. So that's how you calculate F. Then looking at 2.1.2, use Shez's formula, right, to calculate the hydraulic mean depth. Right. As far as the hydraulic mean depth, they do not necessarily have to tell you to use Shez's formula, because you only get what is the hydraulic mean depth when using Shez's formula. Sorry. So using Shez's formula, right, the hydraulic mean depth is denoted as M, and M is equal to the diameter of the pipe, right, divided by 4.
Okay.
Right. That's how you calculate the hydraulic mean depth.
Sorry, sir, on that formula, there is no other one. I think on the formula sheet we have QCD something. That M is the same M, or there is other M, meaning that
QCD.
A square root of 2GHM squared minus 1 is the same.
Square root of. Second.
The formula is saying Q is equal to CD area all over.
Okay, no. That's
yeah.
that's for measurement of flow.
Oh,
That's for measurement of flow.
this thing is confusing. All right, sir. So on chases, we're gonna use that one.
Yes.
M is equal to 4 over D.
Yes. Oh, you are referring to that M squared.
Yeah, that's M squared minus 1.
Yeah, I see. Nah. So it's not the same thing.
Oh, okay.
It's not the same thing. I'll explain that when we cover what is this? Measurement of flow, venturi meters. Yes, it's under venturi meters.
Oh, all right. Okay. We have this formula on a formula sheet, no, where it's coming from this M.
Okay, so to be honest, I don't know the formulas you have on your formula sheets. I always advise students to do as many exercises as possible. That way, the formulas will stick in your head. then that's where you will never have to go to the formula sheet. Because in most cases, if you have to go to the formula sheet, it means you're in trouble. Because if you get there, any and all formulas are going to make sense.
Yeah, because there's like 77 formulas.
Exactly. Right. So it's not about cramming formulas, but if you do enough exercises, the formulas will stick in your head.
Okay.
Yeah. Right.
So
this is how- yes.
I just wanted to ask, for interest's sake, would it ever be that they would ask where they give you the mean depth and then they ask you to calculate via Chess's formula, maybe something else, but they give you the mean depth?
Nah, and they wouldn't do it. It's unnecessary. You know why? Because um, because of how we calculate the mean depth.
Okay.
Right. It's unnecessary because they would have to give you the diameter of the pipe.
Okay,
Anyway.
100%. So.
So if you have the diameter of the pipe, essentially you have the hydraulic mean
I
depth.
mean,
Mean depth, yeah.
Okay, yeah.
I mean, they can do it because they try too much to be I don't know, inventive.
Yeah.
But it's absolutely unnecessary. Hence, I don't think they do it.
We'll follow your lead, sir.
Sure. Right. So this is how you calculate the hydraulic mean depth. Right. Very easy, 2 marks.
Right.
Use Chess's formula to calculate the hydraulic gradient. So that's I. Right. Remember, I said in calculating or in using Darcy or Chess's formula, right, to calculate the to calculate HF, right, you should get more or less the same thing. Right. Now, in calculating the hydraulic gradient, there's 2 Chess's formulas that you can use. One of which is this one. So HF is equal to the length of the pipe times the hydraulic gradient. Right. The other one is V, right, which is equal to the Chassis constant into the square root of the hydraulic mean depth times the hydraulic gradient. Right. So you can use either of these formulas to calculate I. Right. Now, in this case, seeing that they said use Chassis formula to calculate the the hydraulic gradient. Right. Remember, we've already established that the HF, right, using Darcy's formula is the same as the HF we get when using the Chassis formula. So the HF we calculated, right, in 2.1.1 is the same HF we're going to use here in 2.1.3.
Okay.
So essentially you have HF because HF using Darcy is the same as HF using Chassis formula. So we have HF, the length of the pipe, we are still only focusing on 20-meter pipeline. So we're going to use that 20 here, right? And then you solve for I.
Minnie, a quick question. You say when you're using that HF is change of pressure divided by rho times gravity.
Yes.
Must it be the same answer when you're working out with FLQ squared over 3.2 D5? Should be the same answer. Must
Yes.
be the same answer.
It will always be the same.
Okay, no, it's fine.
Okay.
Thanks.
Okay.
It will always be the same. So however you choose to calculate HF, right, it will always be the same.
All right.
It doesn't have to be exactly the same, more or less the same. It's fine.
Okay.
Right. So 2.1.3 to calculate the hydraulic gradients. That one is pretty straightforward. You have HF, right? You have the length of the pipe, which is that 20 meters of pipeline.
Yes.
Right. And then you solve for I.
Yeah.
You get 2 marks.
Okay.
Right. Now 2.1.4 calculate the Chassis constant C. Right. So they're looking for this C here.
Oh.
Right. They're looking for this C. Right. Uh,
1.4.
Now, in
Right.
calculating Chassis constants, right, we must use this formula. Right, we have to use this formula.
Okay.
Now, if it happens that you cannot, or it is a mathematical impossibility for you to use this formula, so meaning that you have too many unknowns, then you can use this one. Right, so you
Oh,
make use
okay.
of this formula only if it is a mathematical impossibility to use this one. Now, if you look at this formula, we're looking for C. We have M, you calculated it here. You have I, you calculated it here. Essentially, we have V. Why? Because we have Q. So if you have Q, remember Q is equal to V times A. Right? Meaning that V is equal to Q divided by the area. Right? So this here is equal to Q so this essentially is equal to Q times 4 divided by pi times D squared. So meaning you can calculate this V using this formula. You have Q is this 20 liters per second, but remember that you will have converted that to cubic meters per second times 4 over pi divided by the diameter of the pipe, which is the 90 millimeters.
Oh,
Right,
that's
so remember
diameter.
also, yes, the D is for diameter.
Yeah.
Remember that this is given in millimeters. You have to substitute it here as meters.
Mm.
So essentially this becomes 0.09 meters.
Mm.
You calculate that, you get V. Once you have V, then you come back to this formula to calculate C.
See. Okay.
So meaning that in calculating C, essentially this will be equal to, so you divide both sides because you're looking for C. It means you're going to divide both sides by the square root of M times I. Square root of M times I. Right?
Yeah.
Meaning that C meaning that C is equal to V divided by the square root of M times I. And then you get your 5 marks. So again,
Okay.
you only use this if you cannot calculate C using that.
Ah. Okay.
That is the only time
But
that
we
you
were
can
given
use
C.
it. Right? Because obviously you can't simply use this formula and then get 5 marks. It doesn't make sense.
So which means maybe if they say in calculate C, but the max is 2 marks, you can use the other one.
You can use this one, yes.
Fair enough. Okay.
Any more questions?
So there was one I came across which says I is equal to V squared over M times C squared. Then when do we use that? Is it the same thing or that's a different formula?
What did it say?
It says V squared over M, the mean depth times the C squared.
Oh, so that's I. So it means they're calculating I. It's the same formula.
We can also use that one, then that's the same thing.
It's the same thing.
Fine.
They manipulated this one. It's the same thing.
Okay.
Perhaps on that one they are looking for the. So I think that one it is when they say calculate HF using Darcy's formula and use Chase's formula to prove that to prove the HF that you got essentially.
Yeah.
So I think that question
Right.
is where they ask you to calculate the frictional head loss using Darcy's formula, right? So you then use either this variation or this one to calculate HF, and then the rest of the question is use Chase's formula to prove your answer. And then to prove your answer, right? To prove your answer, in that case, remember, you do not have HF. You have to calculate HF to see that the HF that you get when using Chase's formula is the same as that of Darcy's formula. So in that case, you won't have HF, so you won't be able to calculate I using this formula. Hence, you'll be able to calculate I using this formula. So in that case, because it is impossible to calculate C using this formula, why? Because you'll have two unknowns. It means C you can calculate using this. Once you have C, and then you calculate I using that. Right, remember this is V is equal to C square root of M times I. Right, if you're looking for I here, it means you're gonna divide both sides by C. Right?
Yeah.
And then that falls away. And then again, because you're looking for I, you're gonna square both sides. Right, that cancels with that, meaning that M times I is now equal to V squared over C squared.
C squared. Yeah.
Right?
Yes, sir.
And then you divide both sides, right, by I, and then M will be equal to V squared over C squared, not times I. So you divide both sides by M because you're looking for I. So this will be M. That is where that formula comes from. Right? When you have to calculate I using this formula.
Okay.
Hence, I'm saying it's the same formula. You are just making I the subject of the formula.
Right.
Right? But we'll look at an example like that one later. Yeah.
Yes, sir.
Right. And that is how you would approach this question.
Okay.
Right. As far as number
Thank
three,
you, sir.
number three is pretty straightforward.
Yeah, very straightforward.
It's a horizontal tapered pipe. Yeah, it's pretty straightforward. Any more questions?
No, sir. No, no more questions, at least for.
How about everyone else?
Oh, yeah, all right, Joe.
Okay.
No more questions, no?
Oh, yeah, two more questions. This is unrelated to the thing. It's just who's setting up the test?
Which test?
The test that we're gonna write tomorrow.
I did.
Oh, okay.
Yeah.
That's neat. Thanks for letting us know. What was question number 2? I spaced on question number 2, but yeah, sorry.
That's right. Just think about it quickly.
Okay. V block roll is the centrist, Chessy's formula. We're writing tomorrow at 6, right, sir?
Yes.
And we can do it at campus or online, whether we choose.
Yes.
Okay. Okay, that's all then. Thank you, sir.
Okay. Anyone else?
Is the paper 1 hour long, sir?
Yes, 1 hour.
No, sir. No, sir.
No, sir.
1 hour, sir.
Yes, it's 1 hour. It's out of 35. 1 hour.
No extra 15 or 20 minutes.
It'll depend on who's invigilating you.
But it's not you.
I don't know. If I will be invigilating, it'll be online, but I have no idea who I'll be invigilating. Remember, there's a couple of subjects that are being written. So if I will be invigilating the online session, I don't know who I'll be invigilating.
Oh, so when it comes to test 2, when are you releasing the videos for the 8-week test? Over the weekend?
Yes.
Okay, what would we be covering?
So we have to finish hydraulic systems So the last section on hydraulic systems is measurement of flow. So I'll do videos on that.
Okay.
And then what is next? I think gear drives. Yeah.
What about cutting machines?
Mr.
Always-
Cutting machines will do after the 8-week test.
Is it not important? Or is there no calculations given, or what?
They are calculated, but we'll do it after 8-week test.
Oh, okay, okay.
So I'm saying we won't necessarily need to do it before the 8-week because I won't include it in the 8-week.
Okay. Fair enough.
But
And
we will do it post 8-week test.
okay, fair enough. Fair enough. So what if we're given a pipe for the hydraulic systems? What if we're given a pipe at an angle instead of just the horizontal pipe?
Well, it'll depend if you've been given the angle, right? So that case is this one, where the pipe is at an angle.
Yeah.
Right. There's the angle theta, right? So use that angle to calculate H2. So if say the water flow is such that it is starting from the bottom going up, it means that will be 1, and this here will be 2. Right.
Yeah.
So if this is 1, you'll get V1, you'll get D1, you'll get P1, right? And then you'll get H1, right? But the bottom, what is this? The what is this thing? The part of
The
the
bottom
pipe,
diameter.
the part of the pipe that is at the bottom, right? H will always be equal to 0,
Okay.
right? And then the upper end of the pipe, you will have H2, you will have P2, you will have D2, and you will have V2, right? So H2 will have a value because remember, if the upper end of the pipe is at this height, it means it is at a height H2 from the ground.
Okay.
Remember here, this is the ground, right? So you will use this angle to calculate H2, right? In that case, they will give you the length of the pipe, right? And then the length of the pipe you take essentially as the hypotenuse.
All right.
And then you are looking for H2. H2 is opposite the angle that you'll be given. Hence, as far as speed ratios, you would then use sine theta.
Sine theta, yeah.
Which is equal to H2 divided by the length.
Length, yeah.
Yeah, therefore, meaning to get H2, it will be the length of the pipe times sine theta.
Okay. All right. Okay.
Aside from that, you simply use the engineering principles that we use under hydraulic systems, which is your Bernoulli's principle as well as your continuity equation. Remember the continuity equation? Q1 is equal to Q2, right? Which is A1 times V1 is equal to A2 times V2.
V2, yeah.
Right.
Yeah.
Yeah. So this we use to calculate either V1 or V2.
What if okay, so what if the flow of water is downward?
Same story.
Same story?
If the flow of water is downward, it just means
we started. Oh, that we
1,
started 2.
and this is 2.
And ended 1. Okay.
So it's same procedure. The only difference is that this will now be 1 and that will be 2.
So no effects from gravity.
So H represents those effects. Potential energy.
I see. Okay.
Remember with Bernoulli's equation, right? You're essentially looking at 3 energies if you are not considering losses, right?
All right. Okay.
You have, say, P1 plus half rho V1 squared plus rho G H1 is equal to P2 plus half rho V2 squared plus rho G H1.
Yeah.
Right.
Yeah.
Each of these terms represents an energy. This represents pressure energy. This
Okay.
represents kinetic energy. And this
All
one
right.
here, right? This is the one that represents potential
Gravitation.
energy. Yes.
Okay. Potential / gravitational energy. All right.
Yes.
Okay. Thank you, sir. That's very helpful. Also, last question, sir. When are you going to upload this lesson onto YouTube? Our meeting. Yeah.
This one.
Yeah, this one that we're recording right
As
now.
soon as we finish here.
Oh, that would be mighty handy. Thank you, sir.
Yeah, as soon as we finish.
Could you just stay on this page on that for a second? I just want to take a quick picture so I can transcribe it later.
That's fine.
Just do a
Thank you, sir,
nice
for the effort.
screenshot. There we go.
Yeah, wonderful. This is exactly what I want. Questions, right? On our sessions, if you can see this one, right? The reason why I breezed through it is because the lessons you've already watched, or at this point, I would hope even that you've watched the lessons.
Most lessons.
Yeah. So because everything I cover on those lessons. So our live sessions will be based on just Q&A or clearing up
Yeah, okay.
and everything that you will have watched from my videos.
Okay.
So the
Right.
test of tomorrow will be looking the same.
Yeah, this is the goal. It will be more or less. So it will be similar questions. That's why I called this document scope, because the questions will be similar.
Just different values.
Yeah.
Thank you, sir. Much appreciated.
Right. Any more questions?
Think so.
No.
I did will be also.
No. That's
What is
that's it.
What is the question?
There's no question, sir.
Oh,
No questions, sir. No questions on our sides.
right. Wonderful. All right then. If there are no more questions, we can end this live session here. It's been
All
a
right.
good
Thank you,
session.
sir.
Thank you, sir.
Thank you so much. Appreciated.
Thank you, sir. Thanks.
Right. It's wonderful. All the best tomorrow. Yeah.
Lovely.
Uncle.
Thank you.
Cheers.
Cheers.
Bye, sir.